Well, hello and welcome again to our journey into complex analysis, and we're in section 6, Cauchy's theorem, and I wanted to have just a brief mention about some integrals involving logarithms. So just to remind you again about logarithms, we know that the derivative of capital log log, this is our principal logarithm, is 1 over z, and it's valid except at z equals 0 and along the negative real axis, where log function is no longer analytic. So sometimes we want to integrate along a contour that crosses the negative real axis. And so our theorems, the theorems that we want to hold, don't hold anymore because the function is not analytic along the negative real axis. So what we do is we take a different branch of the logarithm that avoids this contour. So just to do one simple example of this, I'm going to find the integral along gamma of 1 over z dz, where gamma now is a semicircle from 2i to minus 2i, taken anti-clockwise, and passes through the point minus 2. So here is our contour. It's going from 2i to minus 2i. And it's passing through the point negative 2, and of course it's crossing the negative real axis. So what I'm going to do is, the capital log is not analytic along here, so I'm going to take a branch of log where we lose analyticity over here, and that's well away from our contour. So using the notation we had before, I'm going to take the branch capital log sub 0 of z. I'm going to take that branch of little log log, and that means my capital log log sub 0 of z we evaluate by taking the log of the modulus of z plus I times theta, where theta belongs to the set of arguments but is between 0 and 2 pi. Including 0, excluding 2 pi. And if you look back to what we did on logs, that's going to shift the branch cut across here, well away from our contour, gamma. So finally then, we can now integrate our 1 over z dz along gamma, and we're going to get log sub 0 of z, and we're going from 2i to minus 2i. Now, because we've taken this branch is analytic everywhere except along here, so in particular it's analytic along our contour, and so by what we've already seen, this has a primitive, and it's going to be this logarithm. So I just put in the endpoints and subtract to evaluate this logarithm. Now to calculate this logarithm, we want ln of the modulus. Modulus is 2. Now the principal argument, the argument now of this log sub 0 is between 0 to 2 pi. So this complex number over here now has an argument of 3 pi on 2, because we're going to measure the angles between 0 and 2 pi. This one is a bit easier because this is just again going to be ln 2 for the log of the modulus, and the argument now of 2i is a pi on 2, so this is ln 2 plus I pi on 2 for the logarithm. The ln 2's cancel and I can simplify and I get I pi. So just an example of what you can, how you can do complex logarithms when you can't apply the theorems directly. What you do is you take a different branch of the logarithm so that you have now an analytic function, and then all the theorems apply nicely. And I want to finish this section with just a rather lovely problem. This is further integral techniques that's going to use Cauchy's integral formula. And here's the punchline. We're going to show that the integral from 0 to infinity of the cos of x squared dx is equal to the integral from 0 to infinity of sine of x squared dx. These are important integrals. I think they're called Fresnel integrals, and you can evaluate this integral. It turns out to be root pi on 2 root 2. And the lovely thing is we're going to use complex analysis methods to show this. So here's the detail. We're going to let gamma consist of the boundary of a sector radius r with vertices 0, r, and r e pi on r4, taken anti-clockwise. So here's the picture. So here's our contour. It's an eighth of a circle, so it's a sector with vertices 0, r, and this point here will be r e to the I pi on 4. And we're going to study this integral around gamma. So gamma is going to be this contour. We're going to study the integral of e to the I z squared dz. And out of this, we hope to get these results. Well, firstly, as you see in the picture, I'm going to divide this up into three separate contours. Gamma 1 along the real axis, gamma 2 around the part of the circle, and then gamma 3, this ray going back to the origin again. Now, along gamma, which is the union of these, this is a closed contour. So by Cauchy-Goursat theorem, the integral, this integral we're studying, is 0. It has that value 0. Since e to the I z squared is analytic in and on gamma. Now what we do now is we're going to split this, as I said, into three different contours and examine what happens on each contour. So gamma 1 is pretty easy. Gamma 1, we're back on the real axis, so I'm just putting z equals x into here, and I'm just integrating from 0 to r. And so on gamma 1, this integral we started with just looks like the integral from 0 to r, and I integrate e to the I x squared. So I put z equals x, and x goes from 0 to r. And I can split this, of course, using Euler's formula into the cos of x squared plus I sine of x squared. And this is still a finite integral, so we're adding up this integral here. So we'll leave that one for the moment, and we'll come back to that at the end. Now the trickiest one to evaluate is what's happening along this semicircle here. Not a semicircle, this circular path along gamma 2. And what we're hoping to show is that the contribution to this integral from the bit around gamma 2 actually goes to 0 as r goes out to infinity, which is slightly counterintuitive. You would think as the r goes to infinity, you're going to get more. Gamma 2 is going to get be longer, but it's the contribution of the integral around gamma 2 to this we're going to show actually goes to 0. So on gamma 2, we have to parametrize it. So I'm going to set z to be r e to the I theta, where theta goes from 0 to pi on 2. Now you then substitute this parametrization into the integral. We're going to integrate along gamma 2. So what happens? Well, we have to substitute this into here. So that'll give me e to the I r squared e to the 2I theta. And we're going to multiply the dz by the derivative of this with respect to theta d theta. So you differentiate this with respect to theta, you get I r e to the I theta d theta. Now I want to analyze this thing in here and see what we can make of this here. So if I expand this out using Euler, then I just get this upstairs. And I want to look at the size of this, the modulus of this. I want to see what contribution it's going to make. So the modulus of this, well, I'm going to get the modulus of I r squared cos 2 theta, well that's just 1, times the absolute value of e to the minus 1 times r squared sine 2 theta, and this is positive, so I can ignore the absolute value signs. Now we want to, we can now say then that the size of this integral is less or equal to I'm going to take the modulus of everything back up here. So the modulus of I is 1, the modulus of e to the I theta is 1, r is real, so that just comes out down here, and I'm left then with the modulus of this was equal to that, so I can replace that in here. Now I want to get a little, what's making it complicated is the sine 2 theta, so I want to bound that out by taking theta in the interval from 0 to pi on 2. And if you just draw a little picture of sine theta, and you can see that it's going to be convex in that between 0 and pi on 2, and so this height is bigger than the line joining these two, and that of course just has equation 2 theta on pi, because the gradient of this line is 2 on pi, and that means sine theta is bigger than 2 theta on pi. So I can plug that now into here and say the modulus of this is less or equal to r integral 0 to pi on 4 e to the minus r squared sine 2 theta. I'm going to replace the 2 theta, theta with 2 theta, so I get 4 theta on pi. And if I'm between 0 and pi on 4, so if I'm between 0 and pi on 2, then I'm between 0 and pi on 4, so I can just plug that straight in. And the point is now, this integral I can now do, because it's an integral with respect to theta, so I'm just going to get 4 over r squared, and there was an r out the front, which will make it 4r. I pick up a minus sign, and I'm going from 0 to pi on 4, so when you plug that in, you simply get this expression, 4 on pi on 4r into 1 minus e to the minus r squared, and to our great joy, we see that this is going to 0 as r goes to infinity. This is going to go to 0, this is going to go to infinity, so this over this is going to, the whole expression is going to go to 0. So just enjoy that line, because that's very nice. It tells me that the contribution to the original integral we were studying as you move around gamma 2 goes to 0 as you blow this contour out to, well, if you let r go to infinity. Finally, we have to worry about what's happening on gamma 3. Now gamma 3 is sort of going the wrong way. You want to go that way, so we'll look at minus gamma 3. And then I'll take care of the minus sign in a moment. So I'm going to set z then to be t, e to the I pi on 4. And set that to be e to the I pi on 4. And then where t goes from 0 to r. Then the integral of this function we're studying along gamma 3 now is minus. That's because we went the wrong way along gamma. Then the integral t goes 0 to r. And then I substitute in this, so that's e to I times this squared, which gives me that expression. And then I'm going to multiply the dz, I'm going to differentiate this with respect to t, which is e to the I pi on 4 dt. I can pull that out the front. Now what's happening here, e to the I pi on 2i is a fancy name for I. I squared is minus 1, so I just get e to the minus t squared dt. Now as r goes to infinity, then we know that the sum of all three integrals was 0. The middle one we've just shown went to 0, and so that means the first one plus this one is 0, and I can take that on the other side, and I simply have then that this integral we got from along gamma 1, that must equal this one here, and e to the I pi on 4 is 1 plus I on root 2, when you evaluate it, times e to the minus t squared. And this integral I need to pull out perhaps of the air. This is a well-known integral, that this is root pi on 2. So that the integral 0 to infinity e to the minus t squared, from other courses in calculus you may have done, that's just root pi on 2. Finally then, we can equate real and imaginary parts of this, and so we can now go back and take this thing, and we can equate real and imaginary parts both sides, and so I get cos of x squared dx, the integral from 0 to infinity, is root pi on 2 root 2, because that's the real part, and the imaginary part's exactly the same. By the way, you can just multiply top and bottom by root 2, you get root 2 pi on 4. So that is a lovely, lovely result. We have to work a little bit hard, but it's a good example of the sorts of things one can do now, where we can use complex analysis to answer difficult questions. This is a complicated Fresnel integral. I want to know what is it from 0 to infinity. And it turns out we can evaluate these using complex analysis. And you'll see in the books many other examples of where this sort of technique is used to calculate various real improper integrals. And we'll come back to this question about evaluating real improper integrals later in a much later section, when we have a few more tools in our kit bag. And that's the end of section 6.